We have learned about divergence theorem and Stokes theorem. This relates divergence of a vector quantity, or even better, its volume integral to the surface integral of that vector quantity. Stokes theorem relates the curl of a vector quantity or its integral over an area to its line integral over a closed curve, and this is over a closed volume or closed surface. In this lecture, we are going to look at 2 or 3 examples so that you get familiar with these concepts. So, let us first take divergence theorem. I will work in terms of Cartesian coordinates and then give you problems for other coordinate systems. Let us take a vector field A, which is given as A x y z is equal to 2x x plus 2y y minus 3z z. So, you can see that at any given point it has components, all 3 components x, y and z, right. Let us look at a point somewhere here. It has a component in x and y direction, which are equal, and in the z direction it has a component which is 1.5 times the other 3 components. So, you can see that the field is, if I make this vector, is like this, and as you go farther and farther out is going to be bigger and bigger. All right, and you can make this on all different points. If you are on the negative side, negative is going to be, z component is going to be positive. All right, so you can see that this is kind of diverging, converging or whatever. All right. Now, let us apply divergence theorem to this. So, what we want to show is that A dot ds is going to be divergence of A dot the volume integral. For convenience, I am going to choose a box of size 1, which is centered at the origin. This is its center. So, this is box of size 1, or let us take a box of size L, it does not matter. A cube of size L, so that the front surface here, this is x direction, this is y direction, this is z direction. The front surface here is at a distance L by 2 from the origin. The back surface will be also at L by 2. The front surface here on the y direction is also at L by 2. The back surface will be at minus L by 2, and similarly on the z side the lower surface is at minus L by 2 and the upper surface, this one, is plus L by 2. Let us first calculate the integral A dot ds. Now, when we discuss divergence theorem, remember ds is taken to be pointing out of the volume. So, on the front surface shown by black, the ds is going to be in the direction of x unit vector. On the back side is going to be in the direction minus x. And we have already seen that in the x direction ds is dy dz, x on the back side is going to be dy dz, x with a minus sign. So, for these two surfaces, let us calculate A dot ds. A is nothing but 2x in x direction plus 2y in y direction minus 3z in z direction dot ds will be dy dz in x direction for the front surface, where x is equal to L by 2 plus 2x x plus 2y y minus 3z z dy dz times minus x at x equals minus L by 2. That is the back surface. So, when you take the dot product, these terms are not going to contribute. So, I am not going to worry about them. X is L by 2. So, what you are going to get is 2 times L by 2 times dy dz, which is going to be nothing but the area of the surface, plus 2 times minus L by 2, because the back surface x is minus L by 2, and x and minus x give you another minus sign, integral dy dz, which is also the area. This is nothing but the area of the front surface. And you can immediately see what it gives you. This 2 cancels, this 2 cancels, and you end up getting 2 L cubed. So, the front surface and the back surface area integral gives you 2 L cubed. Let us look at the y direction. You have integral for the front and back surface A dot ds for the y direction. This is going to be integral 2 y dx dz at y equals L by 2 plus 2y dx dz with a, now this plus I am going to replace by minus, because the unit vector product out here is going to be y times minus y for the back surface. So, y equals minus L by 2. Y, sorry, this is a dot product. So, this gave you a minus sign here. This again will contribute to L cubed. And how about then finally A dot ds for the z surfaces, which is nothing but minus 3z, and you are going to have dx dy, and this is going to get at z equals L by 2 is going to be z dot z minus 3z dy at z equals minus L by 2 is going to be z dot minus z. So, this gives you 3 times L by 2 times L square times 2, which is with a minus sign here, which is nothing but minus 3 L cubed. So, if you add all three contributions together, you get 2 L cubed plus 2 L cubed minus 3 L cubed, which is L cubed, which is equal to integration A dot ds. Let us now apply divergence theorem and see if this gives the same answer. According to divergence theorem, A dot ds is going to be divergence of A integrated over the volume, and A being 2x in the x direction plus 2y in the y direction minus 3z in the z direction. You can see that divergence of A, which is partial Ax partial x plus partial Ay partial y plus partial Az partial z is going to be 1. This is constant, so I can take this out. It is going to be only dV, which is where the dV is the volume integral over the cube, which is L cubed. it gives me the same answer. You can also see the power of divergence theorem, whereas in calculating A dot ds I had to do integral over 6 surfaces and got an answer of L cubed. In divergence theorem I got this answer in 2 or 3 lines. So, this is how you can use it powerfully to your advantage. Next, again I take an example for divergence theorem, where I am going to take A to be equal to x x plus y square y plus x y z, and again I want to calculate its integral A dot ds over A cube of side L centered at the origin. So, A dot ds by divergence theorem is nothing but divergence of A dV, and you can immediately see divergence of A is derivative of x component with respect to x, which gives me 1, plus derivative of y with respect to y, which gives me 2 y, plus derivative of z component with respect to z, since that is x y, it does not contribute, and I have dx dy dz. Dx integral, let me write them separately. Dx integral is from minus L by 2 to L by 2. Dy integral is minus L by 2 to L by 2. Dz integral is minus L by 2 to L by 2. First term is a constant, so I get immediately L, L and L contribution from x, y and z, and therefore, I get L cubed from the first term, plus for the second term x again gives me L, z again gives me L, there is a 2, and integral of y gives me y square over 2 minus L by 2 to L by 2. So, this equals L cubed, and this term vanishes 0. So, this is the answer. Let us now check the theorem by calculating the surface integral A dot ds explicitly. Remember, now I am doing it over a cube which is centered at the origin, like the previous example. So, I have x equals L by 2 and backside is x equals minus L by 2. The unit vector on the back side is negative x, on the front side is positive x. Similarly, on y direction unit vector here is positive y, on this side is minus y, at y equals L by 2, and this is at y equals minus L by 2, and on the top surface z, bottom surface minus z unit vector, and this is at minus L by 2, and this is at L by 2. So, when I do A dot ds for x equals L by 2, I am going to get L by 2 times dy dz, because remember A is x. So, L by 2, and for the back side I am going to get minus L by 2 dy dz, but then x dot minus x, and that will make this sign plus. I can remove this now, and this gives me L by 2 times L square 2 times, so this gives me L cubed. So, this is the x part. How about the y part? Let us do it in blue. Y component is y square, ay is y square. So, integral ds ay is going to be y square dx dz at y equals L by 2 minus integral y square dx dz at y equals minus L by 2. This minus sign again arises because on the back side at y equals minus L by 2, the unit vector is in the minus y direction, and this you can see immediately gives me 0. Third term, az ds gives me x y dx dy minus L by 2 to L by 2 at z equals L by 2 plus similar term at z equals minus L by 2. But you see these integrals x and y integrals are odd and integral is being performed from minus L by 2 to plus L by 2. So, they contribute 0. So, you can see immediately that A dot ds is indeed L cubed and that confirms the divergence theorem. Next, I am going to take an example from Stokes theorem, a very simple example. Remember what did Stokes theorem say? It said that if there is a vector field A dot dl around a closed path is going to be curl of A dot ds. So, let us take a vector field A x, y, z, a very simple one. I am going to take this to be 2y x. Let us see how it looks. If I plot it, its direction is always in the x direction and at any point its magnitude is according to y and it keeps on increasing as y increases. On the negative y side is going to be like this. And you can see that, so all these points is going to be bigger. It depends only on the y coordinate. By definition of curl, you can see this field is curling around, or as I said, as a test of curl, if I put a small stick in this field and imagine these arrows indicate the velocity of a fluid, you will see that this will tend to rotate this way. So, you can see that curl is in the negative z direction. Nonetheless, let us check Stokes theorem by taking a unit circle and calculate the integral over this unit circle going counterclockwise. All right. And if I do this integral over a unit circle, this should equal curl of A dot ds. For this unit circle, since this is in the xy plane, ds is going to be in the z direction, and then I am going to have dx dy. The dl, since I am going counterclockwise, right, dl in the Cartesian coordinates is going to be dx x plus dy y. I can also write this as, since this is a unit circle, very simply as just length is r equals 1. So, d phi in phi direction, both indicate the same thing. So, let us calculate curl of A. A is given to be 2y x. Curl of A is I j, I have been using unit vectors x, y and z, partial x, partial y, partial z. X direction is y 0 0, this, which is equal to x component will give me 0, y component will give me 0 and z component is minus 2. So, curl of A is minus 2 z. So, how about this curl of A dot ds? Since curl of A is constant, I can take this out. So, minus 2, I have k z unit vector dot z unit vector, because in the xy plane the vector is in the positive z direction because I am going counterclockwise, dx dy, and this gives me the area of the unit circle, and therefore, this is minus pi r square minus 2 pi. That is the integral curl of A dot ds. Let us now calculate the line integral. For the line integral, I am doing it over a unit circle. A is given to be 2y x, which I can write that as 2 y is nothing but sin phi, x unit vector. Now, we had already seen that s unit vector in cylindrical coordinates is nothing but x cosine phi plus y sin phi, and phi unit vector is equal to minus x sin phi plus y unit vector cosine phi, and therefore, I can write x unit vector as s cos phi minus phi unit vector sin phi. So, A I can write as 2 sin phi cosine phi s minus sin phi phi. A dot dl, we have already seen dl is nothing but phi unit vector times d phi. Let me check if I did that. Yes, I did that indeed here. So, A dot dl is going to be 2 sin phi times minus sin phi d phi integral from 0 to 2 pi. This is minus 2 integral sin square phi d phi 0 to 2 pi, and this indeed gives you minus